Module, which we will start today. I wanted to go back and talk and re-lecture and re-discuss this conversation we had about the van der Waals equation before the end of class on Thursday. I wasn't very happy with the way I described it, so I'm going to describe it again. I kind of hinted at the idea that the van der Waals equation predicts condensation, right? And I showed that as you alternate the temperature, there's going to be a temperature which we call the critical temperature, or TC. You've done some of the homework, you've seen this, which is kind of at the point where the critical temperature is at the point where a gas is actually has the conditions to start to condense. Okay, so actually at the critical point, we'll talk more about this when we get to phase transitions, so it's just a little bit of terminology. But there's a temperature at which, there's a temperature at which above that critical temperature, the system's always a gas. And once you hit that critical point, that temperature is where condensation may occur at a given pressure and volume. All right, and then the idea is that as you cool beyond that critical point, that you're going to have more and more condensation. And the point of the homework problem on critical values and critical coefficients and critical points talks about where this critical point happens for the van der Waals equation, which is this inflection point in the function. The van der Waals function is v versus p. There's a temperature at which there's an inflection point in a curve, which means that the slope and the curvature, the first and the second derivative of the function, is 0. And at lower temperatures than that, you start to get this kind of long, flat region in the middle, kind of at intermediate volumes. That corresponds to condensation, right? The gas and the liquid are coexisting here. I didn't really describe this graph very well, so I want to go back and describe it one more time and clarify it just a bit. And I'm going to do it with just a bit of a visual aid. Imagine that you have a cylinder. Actually, you're going to see this cylinder a lot. We're going to move from boxes to cylinders today. And imagine that inside of this cylinder you have your gas, whatever it is, at some temperature. That's good enough, right? So we'll just say it's at some temperature T. All right, and in that cylinder, we're going to have a nice piston that you can push up and down to compress or expand the gas. Okay, and so what we're going to look at is the response of the molar volume. Remember, this is the volume of 1 mole. Right? How much volume does 1 mole of your material take up? As a function of the pressure, right? The pressure is going to be a function of how much we press this piston down, right? So as we press the piston down, the pressure goes up, right? Because we're making the volume smaller. And we're interested in kind of what's the compressibility? How does the material compress as we push down on it? Okay, so let's look. And so the way that we should interpret this graph maybe is that this is the y-axis. This is the response of the material. And you're evoking a change in pressure, right? So this is decreasing pressure. All right, so just kind of flip your idea of x and y axis around 90 degrees. And we're setting the pressure, and we're watching how the density, or the molar volume, or in some ways proportional to the density of the material, changes. Okay. So what happens at low pressure? Well, at low pressure, which is again down here, the piston is high, right? There's lots of volume. And what do we know about gases? Well, gases like to expand in the available volume, so the gas is going to expand. Right? Which means that the molar volume increases. Right? A mole of your gas takes up more volume at that pressure, right? So that makes that makes sense about here, right? When you're at low pressure, your molar volume is particularly high. So as you start to compress the gas, if we start to push down on this piston, the gas will naturally compress, right? Which means that as pressure rises, the molar volume decreases. And that's exactly what we see. Or maybe we should look at high temperature, right? As you start to increase the pressure, the volume decreases. Okay, but if we're at a particularly high temperature, no matter what volume, how you compress it, it's always going to be a gas. Right? So it just keeps compressing the molar volume decreases as the pressure increases. Okay? But then when you hit this critical point, let's ignore the critical point and look at once we sufficiently cool the gas. At some point, we're going to compress it enough. So what happens now is that as you start to compress the gas more, some of the gas is so compressed that it will condense. Right, so let's say this bottom layer starts to condense. Remember that this just shows the response of the gas. Okay, so the liquid is kind of, we don't know anything about the liquid other than that it exists and that the gas condenses to the liquid, but we don't understand anything about the liquid yet. We're just looking from the perspective of the gas. Right, so what happens now? Okay, so now it starts to condense. You have this small layer of liquid at the bottom. And you keep compressing it. What happens? Well, what happens is that the gas that's sitting above the liquid continues to condense. Right, you get more condensation. But in fact, what happens to the gas, the molar volume of the gas doesn't change. Right, because all of that energy is not going into all that energy is not going into compression of the gas, but rather condensation. Right, so this, let me just kind of mark out these regions. Right, so this is gas only. Right, it compresses like a gas. And then there's this flat region. Notice that as you increase the pressure, the volume doesn't change, right? Or sorry. As you increase the pressure, the volume changes in a flat way, right? And the reason why is because every time you compress more, you're just adding more liquid into more gas into the liquid. And so you get this flat region where the molar volume of the gas decreases almost vertically with respect to pressure, because every time you push the piston down, the gas condenses into the liquid, right? You're just converting gas into liquid. So we often call this the gas-liquid coexistence region. And the idea is that all the work you're doing, all that effort, all that energy you're exerting into your gas isn't going into compressing the gas, but rather converting it into the liquid. Now, once you increase the pressure enough, you have no more gas left. Right? Maybe we've sufficiently compressed it enough, and now you have complete liquid. Now we notice as we increase the pressure, the volume doesn't change. Right? We have a vertical line here, which means that the molar volume is constant as a function of pressure. What that means is that now there's no more gas left. There's only liquid. Right? And what do we know about liquids? Are liquids more or less compressible than gases? Well, I'm sorry? Less compressible, right? Go try this at home. Wow, okay. I don't know how you would do this, but if you try to compress a gas, it's pretty straightforward. You can do it with like a bicycle pump, right? That's the same concept. But if you had a bicycle pump full of water, when it condensed, it's really hard. Right? So liquid is very, very incompressible compared to gas. So the molar volume doesn't change as a function of pressure. So this is liquid only. So the interesting thing is that what we've done to the gas changes as a function of the pressure. Here we're just compressing a gas. Then we reach a region where the gas, as we compress it, all of that energy gets converted into condensation, a phase change. And then we get to the point where we just have liquid and it's incompressible and nothing happens when we increase it. So that's a little different than how I explained it. So it's much easier to think of pressure as your very independent variable and molar volume as your response. And without the idea of attractions, right? The model that we used for the attractions was the Lennard-Jones potential. This is the energetic model we use to interpret interactions across any molecular atom. By adding that in physical size, we get this realistic and physical interpretation of gas and liquids, right? That gas and liquids are the same thing. They're just slightly different in terms of their physical parameters, right? Liquids are more incompressible than gases, but they're made of the same stuff, and you can interconvert between them freely. Any questions about that? Okay. We'll see this again. When we get to phases, we're going to start looking at it from the perspective of the liquid as well. Okay, that's all I had to say about this. We'll look at this much more carefully once we get to phases. I'll leave it up for a minute. Okay, so that's the end of our gas section. Right? So we'll always use gases as an example, as our motivating example, but we won't really talk about them in detail nearly as much anymore. Instead, we're going to start talking about physical processes. Talk about things that we can do with our box of gas. All right, so one of the things that we're going to be interested in is imagine that we have a markers are not working today. Imagine again we have a big box of gas. All right, we have initially a box of gas. Blah, blah, blah. And the question we're going to ask ourselves is what happens to our gas or what happens to our system when we change the size of the box, right? Or anything about the box. Maybe we want to compress the box. To a little tiny box. Maybe, for instance. Or maybe we want to fill the box more. We want to increase the amount of material in it, but holding the volume constant. Another way to think about that is we're holding the volume constant, increasing the pressure. Here we're increasing the pressure by reducing the volume, and so on. Right? And the question is how does the energy of our box change as we change the environment? All right, so far we've only looked at static boxes, right? We've fixed the box to a volume, number of moles, and temperature. And we haven't really talked about changes, right? I mean, we've kind of looked at changes, right? We've looked at how pressure changes with volume here. All right, but we haven't really talked anything about energy, right? How does the energy of the system change as we move across this curve, for instance, right? And unfortunately, we just don't have the tools yet to do that. But today I'll introduce those tools. We're going to, over the next 2 weeks or so, we're going to learn 3 laws of thermodynamics. And these 3 laws together will allow us to basically track or calculate changes in a system in any arbitrary way, right? Just like Newton's laws of equation allow us to solve for the motion of any particle, the laws of thermodynamics allow us to track a system of any type or any change, assuming the system's in thermal equilibrium. Right, just like in Newton's equations don't work for things that don't work with Newton's equations, or relativistic motion, for instance. Right, there are going to be limitations to our analysis, but we have to come up with a set of rules. And the first law of thermodynamics is the one we'll talk about today. Let me go ahead and erase this over here. Right, after all, we're chemists. Inevitably, we're going to ask the question, well, what happens to our box if we put 2 different things in here that react, right? Do they react? How fast do they react? And how much energy does it change? We're going to ask those questions. But before we get to that, let's think about just changing the system itself, right? Just changing the box. Right? How does the energy of our system change? And the law that we're going to start with is the first law of thermodynamics. And there are many different ways to write this. All right, and so I'm going to kind of list 2 definitions of the first law of thermodynamics. And they give the same answer, but they have slightly different interpretations. The first one is that the internal energy, right, that's all the energy contained in our system internally, which I will always write as U, of an isolated system. I have not defined what that is yet, but I will. Talk about that in a second. System is constant. It's unchanging. Or, if a system is in thermal equilibrium with another, the total internal energy, which I'll write U equals U1 plus U2, right, for the two different systems, is conserved. Now maybe this isn't that, or is constant, however you want to think about it, right, is constant. Conserved and constant mean the same thing here. So what does that mean? Well, the first sentence is pretty straightforward, right? We have to define what an isolated system is. But the idea is that you have a system set at some temperature. It's isolated, which means it's not interacting with anything, right? It's just going to stay the same, right? It's going to be the same temperature, same amount of energy. Nothing's going to happen, right? It's the same for all of eternity, right? Interestingly, though, if you put that system into equilibrium with another box, so maybe a good example would be our box, but it's interacting, and the other system is the room that the box is sitting in, right? It can exchange heat with the outside. Then the total energy is conserved between the box and the room. Notice that not each one is constant, but the sum is constant. What that means is that the system can transfer energy from the box to the outside or vice versa. And the sum is always the same, but you can move energy from one to the other. That's going to be really important, right? If we want to do anything, we're going to have to move energy around. And the idea is that as long as everything's in thermal equilibrium with each other, then we conserve energy amongst all of the bodies. But this isn't a very practical statement, right? This is a kind of an obvious, not an obvious statement, but it's just a truth. But there's not much we can do with this, right? So there's a different definition that's much more useful that we'll use all the time. Okay, this is the real one. But it's less conceptually interesting. So in a system undergoing a change, undergoing some process, all right, doesn't matter what it is, the change in the system's internal energy is equal to the sum of the work, W, done by or to the system, and the heat, Q, or heat Q, exchange between the system and its environments.
Everybody who gave me a name on this list, just one more time, just make sure you try going on to these announcements, right? You've gone to this link right here in the announcements. You clicked on this.
Well, we can write this in one little equation, right? That the change in the internal energy is equal to Q plus W. This equation will allow us to do just about anything in this class. Doesn't seem like it, right? Because we haven't really talked about what work is or what heat is or how we measure them. But we know if we can always think about changes in energy as long as we can think about changes in heat and changes in work. So let's talk about what those are. We've kind of jumped around the idea of work. Right? I've talked about work as the idea of mechanical motion, right? The idea of you're pushing something, right? pushing a person pushing a box that weighs a kilogram across the meter. 1 meter is a joule, right? And so that's work, right? So work is just that. Energy expended, or let's say energy transferred in and out of a system. By use of an external force. All right? Just like pushing a box, right? We're doing work on the box by pushing it, right? We're applying a force to the box and making it move. We can think about work as applied to our gas, a box of gas, as what we call an orderly motion. So here's our box. And let's say we apply work or energy. Draw one more. Ooh, these are really bad. Okay. All right, we apply energy to our gas. Let me draw the gas particles of a different color. And we all make them move in an orderly motion, right? We're pushing the gas. Compressing the gas, if you will, right? This is work, right? We're making orderly motion. Okay, we're going to look at different types of work, right? A really great example, once we get to heat and we can look at the differences, we can immediately start thinking of different examples of work and heat and how they're transferred and how they apply to a process. But a really classic example of work is you take a gas that's in a piston, right? And you compress that piston and compress the gas. That's work, right? You're pushing all of the particles of gas in an orderly way as you decrease the volume, right? That's doing work to your system. Chemically, work can be represented as a reaction, right? Reaction is a work, right? Reaction is work, right? You're doing orderly. You're using energy to do an orderly process to convert one chemical into another. That's chemical work. Right? Anything that's orderly. Heat, however, is much more. What's the word I'm looking for? Ethereal, if you will. Abstract. Right? We can see work because we can do it. Right? You know how to do that, right? I'm doing work on this marker as I open and close the pen. But what is the heat generated from this process, right? It's not clear. So what is heat? So heat, Q, is energy transferred in and out of the system Now, this is actually what the textbook says, and it drives me nuts, but I like mentioning it anyway. In and out of the system, not by external forces. So it's all energy that isn't work. Okay, that's not very helpful. But it's true. It's true. You're gonna, for instance, you have this magic energy measure, right? You know how much you're compressing a gas and you're pushing the gas in. You know how much work you're doing, but you measure a larger energy change in the amount of work you put in. Well, that rest is heat. Okay, so generated is heat. But what the hell is heat? So there's a couple different definitions of heat that I want to give. So I'm going to go ahead and erase this here. I'm just going to leave up this right here because this is the real law. Let me rewrite it at the top. All right, the change in energy is heat plus work. All right, so let's think of some definitions of heat. So first I want to talk about a macroscopic definition of heat. There's a really good way there's a really easy way to measure heat macroscopically. Heat is the energy in the system measured by a thermometer. This is the energy that's in the system, right? Measure, you have your box of gas, right? Box of gas has energy in it. It's not doing anything. There's no meaningful action, right? There's no work occurring to your box of gas, but you measure it and it's got some energy in it because you measure a temperature. Well, that's the heat of the system. Right? So the total internal energy of a box at rest at some temperature is all Q and no W. Some ways we could call heat is a energy primitive, right? A primitive form of energy does not have any particular use, but it exists. Or the energy left over that cannot be used for work. Not very helpful, but it's true. Maybe a different way to look at it is microscopic. All right, let's zoom in at the chemical level, at the atomic level. A transfer of heat is a change in the, sorry, that's change, not charge, in the motional state of molecules, right? Or atoms. It is the sum of all energy used in the random motion of particles. Next semester, we'll define the different types of motion that particles can have, but they are translational, which means motion in space, X, Y, and Z motion, rotational, vibrational, and electronic. Okay. Molecules can, for instance, can vibrate, they can rotate, they can move in space, and they have electronic transitions, right? If you ever put a molecule in a UV vis spectrometer and seen absorption, that's an electronic motion, right? You're seeing excitation of an electron. Right, so we have to account for those as well, right? These can be random. If you have molecules that are really, really hot, right? This is something that you don't often see. But when you have a normal molecule liquid that you put it into a UV vis spectrometer, almost all of those molecules are in their electronic ground state, and you need a photon of light to excite them to an excited state. But if you crank the temperature up really high, often you'll find molecules in excited electronic states just randomly, right? There's enough energy in the system that they can be in an excited electronic state. You often see this, for instance, in interstellar medium. Like, for instance, in the sun, most of the hydrogen in the sun is ionized. It's H+. And in some ways, H+ in ionized state is the most extreme electronic state you can have because you kick that electron completely out. And there's very little normal hydrogen, much less H2 in the sun, but there's lots of H+. Right, so we have to account for those things. Right? That's what it is. It's just the motion of particles. There's one more definition I want to give. And this one's going to apply when we learn the second law in about a day or in a couple lectures. Heat is proportional to entropy. I haven't defined entropy yet, but we will. Which is the measure of all possible arrangements of a system at a given temperature. Let me tell you what I mean by that. This is actually really interesting. We'll come back to this with entropy because we'll define this exactly. We're going to find that entropy is the way that we can track experimentally heat. Right? So entropy is somewhat like the measurable of heat. We'll talk about that more. But let me talk about what I mean by the arrangements of the system. For instance, let's look at our box of gas. Let's just keep it very simple. We just have some particles in there. What do I mean by arrangements? Well, for instance, one of the arrangements is that you have all the gas particles in a beautiful lattice. right? They're equally spaced. They look like a crystal, right? That's an arrangement. What's another arrangement? Well, one of the arrangements could be that it looks like an elementary school dance, and you've got half the crowd on one side and half the crowd on the other side looking at each other awkwardly, right? Those are all reasonable arrangements. Another one might be that they're all on the left side and none on the right side. Or maybe one of the particles is weird as one by itself, right? Right? These are arrangements of the system, right? You can imagine that every time the box, everything's moving at random times, and if you take a little time step, right, and look at the box, you're going to see some random arrangement of that number of particles in the box. And these are all possible arrangements. To get these would be incredibly rare, right? To get everything organized like this. As we'll learn, this is incredibly rare, but it's possible, right? And what Boltzmann, this is what's called the Boltzmann's definition, is how Boltzmann defines heat. Boltzmann says that if you count the number of possible arrangements, right, which is the number of possible ways to arrange all these gas particles in a physical space, and you ask how much energy does it take to measure each one of these, right? How much energy does this represent, right, of arrangement? Right? How much energy does it take to go from a random state to this state, or this state? If you sum over all of those, that's the total heat of the system. Right? Heat is just a measure of randomness. Not surprisingly, when you're at 0 Kelvin, heat is 0, or effectively can be 0, because there's only one possible arrangement because there's no energy, right? So heat would be 0 at 0 Kelvin, and as you raise the temperature, there are more possible arrangements of your atoms, and the heat increases. It's a statistical thing. Note that this kind of motion, right, this motion of arrangement, is not doing work, right? Because the system is sampling all of these different arrangements randomly, right? So it can't actually do anything meaningful with this. It's just like you have a bunch of particles moving around freely, randomly, and they're going to arrange in something, and you can't stop it, right? You can't do anything with that arrangement. And the energy that it takes to do that randomness, to keep that randomness going, is the heat of the system. Okay, so it's just statistical. Any questions about this so far? Okay. So don't worry about it too much. If this seems unintuitive, that's okay. Because when we get to entropy, which is the second law, we're going to be able to measure heat as a function of the entropy. Entropy is proportional to heat. And we'll talk more about entropy and how you measure it, right? And then it'll become more clear what heat really is. But we're kind of walking this path that historically happened. An interesting story, and I'll show you a picture of it in a couple lectures. Maybe I even have it here. I might not. It might be... Yeah, I'll have to go dig it up. I think it's in one of my presentations. For a long time, physicists, or scientists in general, I mean, they knew about work, right? Because the Industrial Revolution, everyone's always had mechanicals, right? You can think of a wheel, right? Everyone knew you had to exert energy to move a wheel, right? Since the dawn of man. So the idea of work is very straightforward, using energy to perform an orderly process, right? So it's very clear. But of course, anyone with an oven or a fire would know, well, my fire's doing some work, right? It's reacting molecules and combusting them, but it outputs some energy that you can feel on your body, right? Heat. And for centuries, we understood these two concepts, but we didn't understand that they were the same thing, right? It was never clear that you can take heat and convert it into work, or vice versa. Well, you could take work and convert it into heat. That's pretty easy, right? You can, when you run, right, you're doing work and your body's generating heat. You can feel it transferred into heat, physically. But converting heat into work was not clear at all to anybody, right? And in fact, it wasn't until the Industrial Revolution, right? That's one of the reasons why the Industrial Revolution, one of the key realizations about the Industrial Revolution, like what jump-started it, was the fact that they realized that you can convert heat into work. What's a good example of something that converts heat into work? Well, let's hear what here. I just heard something, and I'll ask you, Megan. What was this I heard over here?
We had the same thing.
Oh, what was it?
Steam engine.
Yeah, a steam engine, exactly. A steam turbine, right? you do work on your water, right? To heat it up, to boil it, you're doing work, right? You're converting a liquid into a gas, which releases heat, and you use that heat to drive a turbine, right? Right? Any power plant works like that, right? A nuclear power plant, for instance, you don't actually get energy from nuclear reactors directly. What you're doing is that the heat of fission is converted into heat. The work of fission is converted into heat through water, which then spins a turbine, right? You're really getting turbine power, hydroelectric power from a nuclear plant, but the driving force is the energy of fission, right? The work being done is fission, but you're not actually getting that from you're not actually getting the work directly delivered to your homes. Right, so it wasn't clear at all until, the late 1700s that these were interconvertible. This says nothing about them being equivalent. Right, we knew that they were interconvertible, but it wasn't even clear when they realized it was interconvertible that work and heat are the same thing, right? They're made up of the same stuff. Right, this concept of using that work as an orderly motion and heat is a disorderly motion is not obvious at all until the 1800s, right? And a man named Henry Joule, the namesake of our favorite energy unit, and I'll show you his experiment. He actually created an experiment to prove that work and heat were the same. Right? He did something that did work by generating work and did something by generating heat to convert it to work and showed they were the same thing, equivalent. We'll talk more about that. Right, so it was never obvious to anybody that these were the same thing or how they correspond, right? And the thing I want to drive home is that the difference between work and heat is about order and disorder. Right, we're going to see that time and time again. Right, that we can order something to do work, but sometimes when we do work, it generates disorder inherently, right? So you always generate heat. And what we'll prove, in fact, is that you can't convert 100% of heat into work or vice versa, right? There's always some loss. So we'll learn that as well. Okay, so let's talk a little bit about this equation. What can we do with this equation? And I want to start with, we want to look at energy changes, right? We want to do something with our gas. And let's do some calculations, right? Let's think about, let's make a change to our gas and ask ourselves how much energy does it take to do it? How much energy does it release? Or how much energy does it absorb? How much heat does it evolve? So for the next couple lectures, we're going to talk about pistons. Because pistons are really a nice way to talk about work and heat. So let's imagine now, let me make sure I have everything drawn properly. Yes. Let's say we have a cylinder. Okay, that one's dead. Okay, here's our cross section of our cylinder. I'll make it look somewhat circular. Okay, and then our cylinder, right, we're going to have this tall cylinder. Here's our bottom of our cylinder. And somewhere in this cylinder, we're going to place a piston. Right? And a piston is just another cylindrical object that seals the container and sets the volume of the container. So here's our piston. Okay, so let's say, for instance, we apply a pressure to the piston, a constant pressure. Okay, all right, we're just going to push down on it at a constant force. All right, so let's say we apply PEX, external pressure. Right, this is our external pressure. I'll just write that here. All right, this is just the force of your hand. All right, we can define a few things. Right, the area, right, the surface area of the piston is A. This has volume. Right. and it has some pressure. Okay, and we have a gas in there, of course. There's a gas in there. It doesn't matter what the gas is. Well, let's think about how much work is being done on this system. Okay, we have a gas, we're compressing it, right? Or we're expanding it, depending on which way we move the order, the sign of the pressure, the force, right? If we're moving it up, we're expanding it. If we're moving it down, we're compressing it. Physics tells us that the work being done is the force times displacement. Okay, so that's just the basic rule of work, right? Applying a force and we along a displacement, right, which is the motion of this piston going up and down, and that's the amount of work that we do. Okay, so now let's think about this a little more elegantly. Okay, we want to calculate the change in work, and we want to do it in a smooth way. Okay, so what we want to do is we want to move the piston just a little bit at each time. Right? Just small little displacements. All right, so with small displacements, we can say that the small change in the work, delta W, all right, we're going to do a constant force, right, a constant external pressure, is the magnitude of the force times a small change in the displacement. Okay, we're just going to do a little bit of calculus. Now, we don't have anything about the force here, but we do have an area, or we do have a pressure, right? So how do we convert pressure to force? Well, remember that pressure is defined as force over area, which means that force is pressure times area, right? Which means that the displacement of the work after a small change is going to be the external pressure times the area times the displacement. Now, here's something that's really interesting. Let's look at the units of this for a second. So pressure, again, is in pascals or newtons per meter squared. Okay? But what are the units of area?
Get a volume.
Right, exactly. Right. We have x squared, units of length squared, times units of length. Right. So the idea is that dV, let me draw it real quick. So if dx is this distance between the initial position and the final position, then A times dx is going to be the volume created by the displacement. Kind of the region of the cylinder where basically for where the piston was originally to where it is finally, right? This region in the middle is a volume. Right, so this is going to be P ext times the change in the volume. We've seen this before, P times V, right? You see it in Pivner, right? This is the energy required to maintain the pressure and the volume of a gas. But now we're doing it in a slight with changes, right? So we have a factor of D. We have a dV instead of a V here. Now here's the problem. Pressure and volume are not just independent variables of each other. These are functions of n and t and so on and so forth. Right, they're functions of many variables. Right, so now the question is that if we want to calculate how much work is being done as we move the volume of, as we change the volume of our of the container, right, of our piston, as we apply a pressure, we need to make sure that we understand how we're moving in the space of the other variables. Let me write that down. This is kind of a tricky point. So if you were given this equation, and this were calculus 1, I would say, okay, in order to calculate the total change in work as I compress the piston, is I would integrate both sides. So you have an integral of work. Right? You integrate over all the small changes in work to get the total work, and you integrate over the change in volume to get the other side. But here's the problem. Work is a function of T, N, V, and P. Imagine now that I draw, this is going to be a really hard thing to draw, but I'll try my best. Let's imagine, for instance, we have work as a function of, so let's do this as work in this axis, and temperature here, and volume here, for instance. And let's say there's a surface, right? There's going to be a surface. It's a function of multiple dimensions. Right, and depending on the, right, and I'm going to write like a contour map. Depending on on which region you're in, you might have a higher amount of work in one region and a less amount of work in another. I think of this as a topographical map, right? Where x and instead of land, you have temperature and volume, and the z-axis, the height, is the work or the amount of energy in that region. So let's say, for instance, that I start here. This is my initial point, and I want to go here. Well, which way do I go? Well, I can go like this, right? I can take a path along this axis, or I can just draw a straight line, or I can do a loop-de-loop. Right? There are many different paths along this function to go from one point to another point, to the initial point to the final point. And so in order to be able to integrate work, I have to know which path I take. So what I should say is that the integral of the change in work, which would be the total work being done, is path dependent. Because work is a multivariable function. There are going to be some paths that require a lot of energy to move from point 1 to point 2. Right? The piston equivalent of this would be, would I just move it slowly like this? Or will I go like this? Or will I spin it, or rotate the whole thing around? You can think of a bunch of different ways, crazy ways to compress this. Right? But it's path dependent. So I can't actually just integrate it because I need to define the path. Okay? And so that's a problem because that really makes our life complicated, because what we want to do is all we care about is we have a piston that we want to move from here to here, and we just want to know how much energy comes out. But if the temperature changes, right, depending on how the temperature changes, the energy will change. Depending on how the moles might change, like if you can exchange mass in and out, right, out of the cylinder, that would be a problem, right? There's all these different variables that we have to deal with. Okay, so what we're going to do now is we're going to say, okay, well, let's make an assumption. Let's simplify things a little bit. And let's fix some things so that we have a fixed path. Okay? And so instead of worrying about all these functions, all these different variables that might change as we move from point A to point B in our piston, let's fix some things. and make them constant and see how the mass simplifies. So let's try that. The first one I want to try is what's called isothermal work. So what we're going to do, what time is it? Okay, good. We're going to fix temperature. Now the easiest way to fix the temperature of our piston is to put it in a bath. And allow it to exchange heat. So that we have a bath at T bath, and the system can exchange heat. Right? So the system is always at the bath temperature. Sorry, I switched from red to blue. Okay, so that means then, in this crazy graph that I drew, that temperature doesn't change, right? So so when we go from point A to point B, we're not going to move along the T part, right? We're only going to move along the V part. Right? That'll simplify our math considerably. Okay, so then what that means now is that the change in work is now just a function of volume. Work is now just a function of volume, not temperature. It's just a single variable. We integrate both sides, px dv. All right, and we want to integrate from the initial volume to the final volume, vi to vf. So we're going to take it from the initial volume, we're going to compress it to the final volume. All right, we're going to hold the temperature constant. Since the temperature is constant, we can convert PEXT to volume by applying a gas law, a state equation of state. Right, because we want to integrate pressure with respect to volume, so we need to express pressure as a function of volume. Right, so we can just use the ideal gas law, for instance. Right, so that's the integral from VI to VF. Right, pressure is equal to nRT over V. So nRT bath over V dV. Now notice I have integration bounds on this integral, VI to VF, but I don't have them here. But we could write VI to VF, and I'll show you what that gives us in just a second. Right. So now let me just rewrite this here. We'll finish this integral up. Right, we could also apply here the van der Waals equation too, right? It doesn't stop us. Any equation that expresses pressure as a function of volume for our gas, we can put it in. But for now, we'll just use the ideal gas law because it's easy. All right, so we have, let's do the left-hand side of our equation, which is the integral from VI to VF of work. This is going to be the work, or the energy of the system at VF, minus the work of the energy of VI, which is delta W, right, the change in work. And this is equal to the integral from VF to VI of nRT over V T bath dV. Right, I'm going to factor out some, these are just numbers, right, because the temperature is constant. So this is nRT bath, integral from VI to VF of dV over V. Does anyone know what this integral is? Integral of 1 over x? ln of x. Very good. That's nRT T bath times ln of VF minus ln of VI. And we can write that as, so let me just write it out. So change in work, isothermal, right, it means constant temperature, is nRT ln VF over VI. Remember, the difference of two logarithms is the logarithm of the ratio. Just as a reminder, if you don't remember that. Ln A minus ln B is ln A over B. Ln A plus ln B is ln A times B, and so on and so forth. There we go. Right, so now we have a function. We can now calculate the amount of work, the amount of energy it takes to take a gas at a constant temperature from one volume to another. Right? And it's just nRT times the logarithm of the volumes. Notice that this is completely independent of the gas. Right? Every gas compresses exactly the same. Ideal gas. Right? Just like we saw before, right? Every ideal gas does everything exactly the same. And that's no different here. There's nothing here about the physical properties or the physical behavior of a specific gas. It's completely universal. Right? Not surprisingly, there are some gases that are easier to compress than others, but we can't account for that with the ideal gas law. Right? We would want to instead apply the van der Waals equation here. And then we would have an expression for the amount of work being done that's a function of also of the gas's physical properties. Right, so this gives us a really, really nice formula. We do a lot of things isothermally. Later, once we do it, we'll talk about the internal combustion engine. There are multiple isothermal steps in the internal combustion engine. Right, that's why we use oil to keep our... Right, that's one of the reasons, well, there are many reasons why we have oil and coolant in our cars. Oil, of course, helps things lubricated, but it also helps cool an engine. And the idea is that you use the oil or your antifreeze as a constant temperature bath. Right? As we know, your engine generates a lot of heat because of the reactions that occur within the combustion chamber. Right? And there's also compression of gas. Right? You're compressing gas and expanding gas. Right? That's the whole point of combustion. That generates quite a bit of heat and also requires a lot of energy. And in order to do things isothermally, which is the most efficient way of doing it, we got to keep a constant temperature, right? That's why antifreeze exists. It's one of the reasons. The other reason is not to have your car blow up too, but temperature moderation is just as important as keeping a low temperature. Right? Keeping a constant temperature is a big deal because the idea is that a reversible isothermal compression or expansion is the most ideal compression. Let me explain what I mean by that. And what I mean by ideal is that least amount of energy required. Let me give you an example of what I mean by that. Let's find my notes. Let's, for instance, look at a compression curve. So we're going to measure volume of a gas versus the pressure of the gas. Okay, and we're just going to do it for an ideal gas. It looks kind of like this. Okay, so this is what we're doing to our gas. We're going to fix it at a temperature for now. Okay? We're not going to do anything. We're just going to hold it in a bath and we're going to compress it. I want to take away this idea of reversibility. Reversibility means infinitesimal change. Right? This means that we're using little dx's, right? It's little things we can integrate over. Right, so let's imagine we don't have a reversible expansion. We have an irreversible expansion. So for instance, let's say this is our initial point right here. And here's our final point. Okay, and let's do this. So this is an expansion, of course, right? So we're releasing our piston here. And let's do it irreversibly. What I mean by that is we're just going to lift the top off and let it blow. Okay? To the final volume. Okay, so we're not going to slowly move it, we're just going to yank it out. So if we yank it out really quickly, the volume's going to change initially from VI to VF, but the pressure hasn't changed yet. So the pressure is going to move like this to here. Okay? And the total amount of work you're going to do is pressure times the change in volume, right? Remember, dW is PdV. So dV is VI minus VF, so delta W is P, whatever this initial pressure is. We'll call this PXT. Times the change in volume, which is VF over minus VI. Right? This is just the area here. Right? This is the irreversible area. Okay, so when you blow the top off, the amount of work that it does is VI minus VF, the difference in volume times the pressure. So it's the area of this square. Now let's look at a reversible expansion. Same graph. I'm going to draw it in black this time. Something like that. Now what we're going to do in a reversible expansion, this is irreversible. And we'll do reversible here. We're going to move the volume tiny amounts and let the pressure equilibrate. We're going to move it tiny amounts, let the pressure change. So what happens? Well, maybe we make a little small change here. We go to there. Here's our first step. And then let's go to our next step. It'll be here. And maybe our next step is here. And so on and so forth. Right, we can just keep going down the line, right? And when you make infinitesimal steps, the change in work per step is going to be the change in the volume times the pressure. All right, so for each step, the work being done is just this area right here, the area right here, area right here. Right, and we can go all the way to the end, and we'll find out that the area is roughly the region under the curve, right, the integral. But you see the difference here? When we do a small compression, or sorry, a reversible compression, a slow compression or expansion, the amount of work we do is just the area under the curve. But when we do an irreversible expansion, which is where we just pop the lid, we're doing this extra amount of work right here. I'll just color it in. The system releases an extra amount of energy. Now, if this were a bomb, right? This is why bombs aren't particularly good when they're reversible explosions, right? Of course, there's no such thing as a reversible explosion, but imagine that you had a reversible explosion where it just explodes a little bit at a time. The amount of energy that you generate along this process is smaller than you would be if you irreversibly exploded the bomb, right? The difference is the area above the curve here that you gain. Right, so this is kind of a double-edged sword. If you want to do a compression, right, you have to exert energy, and the slower you do it, the more efficient it is, right? But if we did an irreversible compression where we just go bang like that, we're doing all of this extra work here that's being represented by this area above the curve, and it's actually less efficient. Right, so the idea of doing a reversible compression is the most efficient way to do a compression, or any sort of work, right? That we want to do things slowly and reversibly, right? Not irreversibly. Right? Unless you want to do as much damage as possible, then you want to do it irreversibly. Right, so it's just a little bit of calculus, just a little bit of area under the curve. Any questions about that so far? Okay. So one of the things that we're going to find is that when we talk about the efficiency of a process, right? How much, for instance, Maybe we gain some energy from a system through heat, right? And we want to convert it into work, right? We have a steam turbine, right? We generate steam through heat, and we convert that into a turbine that spins that allows us to compress this piston, right? When we talk about efficiency, we're going to realize that in order for a system to be efficient, as in the maximum amount of heat converted into work, you have to do everything slowly and reversibly. Because if you don't, you're always going to consume this excess amount of energy, and you're going to lose your efficiency. What we're going to find, of course, is that not surprisingly, it's impossible to make a perfectly efficient engine. And the reason why is rather interesting, but we won't be able to talk about that until the second law. Okay. So the idea is again, the more irreversibly we do something, the more energy that you're either going to release or expend because of this kind of area kind of concept, right? So a good efficient process is a slow one. But this isn't the only kind of way that we can integrate work, right? Again, remember we came back to this idea of going isothermal because we can't integrate work because it's a weird function of many variables. So we have to limit the amount of variables that we analyze the work over. Okay, so we've done temperature, and just for the last 10 minutes, I want to introduce one more, which is another very, very common one in chemistry. We're going to allow the temperature to change. But instead, we're going to fix the other variable in our graph, volume. So a constant volume process is called an isochoric process. Okay. A good example of a constant volume process is one that's done in open air, right, where there's no compression going on. But we've got a problem. Remember that we've said that work is equal to pressure times the change in volume. Sorry, the change in work is the change in pressure. Sorry, let me rewrite that. The change in work is the pressure times the change in volume. Well, what's the change in work if volume doesn't change? 0. So if dV is 0, isochoric, the change in work is 0. Any sort of process where the volume is constant, there is no work being done because it's impossible. Work is being done in an orderly fashion. And if you're not doing something in an orderly fashion to a gas or a material, which is changing its volume, its physical characteristics in an orderly way, you're not doing any work. So in fact, in an isochoric process, the change in the internal energy is just a change in heat. A good example, actually a better example of an isochoric process is a pressure cooker. If you're cooked in a pressure cooker, you probably would understand, you may understand this idea, right? When you put a thing in a pressure cooker, right? As you change the heat, as the temperature starts to increase, the pressure increases, right? But the volume doesn't, right? And all that you generate, you're not doing any work on your rice or your whatever you cook in a pressure cooker, chicken. You're just generating heat, right? You're just cooking the damn thing, right? In heat. It's not doing any work; it's just doing pure heat. So only the temperature and pressure can vary. But now we have a problem, right? We don't really have an equation for work, or for heat, right? We had a nice one for work, right? Pressure and volume, but we don't really have that concept for heat. So we've got to go back to our definition of heat to think about it. And the definition that we should use to think about heat is that heat is what we measure with a thermometer. So if we were to measure the change in a heat, In a system where the energy change is only heat change, we should just measure the change in the temperature. Since work is 0, all energy change is heat change. So we can write that the change in heat, dQ, is proportional to the change in the temperature. Emphasis for isochoric. So we can write now, because they're proportional to each other, they're only different by a constant, right? So that the change in heat, right? I'll write sub V, that's constant volume. I'll write that here. Is equal to a constant C times the change in temperature. Now let's think about what the units of that, oh, this is not time, sorry, temperature. Let's think about the units of C. Well, the units of heat are joules, and the units of temperature are Kelvin. So C must have units of joules per Kelvin. Does anyone know what has the derived units joules per Kelvin? It's maybe not obvious. Maybe an engineer, if there's an engineer in here.
Specific heat?
Specific heat. This is the specific heat. Specific heat is how much, it's a material dependent quantity. I'll define this real quick. The specific heat we haven't gotten there yet. But yes, you do. This will be all, well, yeah, so we could do this. How about that? Per mole, right. Yeah, we should have a factor of N here too as well. NC delta T. Yeah. But yeah, sure. You can think of this on a per molecule basis as well. But you're right. Specific heat is the energy required to raise the heat or raise the temperature by 1 Kelvin at constant volume. We're going to learn there's also a specific heat at constant pressure too, but we'll get back to that. Right, so then we know we don't have to do any calculus here, right? There's no calculus that needs to be done. For a isochoric process, a reversible isochoric process. So a reversible, let me just write these down. Isothermal process. The change in energy is the change in work. Work is equal to, the change in work is equal to nRT, and then F over VI. And for an isochoric process, a change in heat is the specific heat times the change in temperature. Okay, well that's really easy. I'm pretty sure you've seen this calculation. Maybe you've seen this formula in general chemistry, right? When you talk about how much energy does it take to raise the temperature of liquid water by 1 degree, right? In fact, that's the definition of a calorie. A calorie is the amount of energy required to change the temperature of liquid water by 1 Celsius. STP. Right, we call this the constant, the heat capacity. We want to define the heat capacity a little more carefully the heat capacity is always defined as the change in the energy with respect to temperature at constant volume. All right, this is new notation. We have a derivative of energy, right? The change in energy as a function of the temperature at constant volume. It's really easy to calculate. We can just measure the temperature, look at the energy, take the slope, and we get the heat capacity. Okay, we're out of time today. So what we're going to do now is to take these ideas, right? We have some very simple equations that allow us to measure the energy change as we change our box with two different things. We'll talk about a couple more on Thursday, a couple more simplifications. And then what we're going to do with that is we're going to realize that we only have half the picture. And we're going to want to ask ourselves, well, maybe we generate some heat and we want to convert it into work, right? Maybe we have an isochoric process that generates heat, right? A water steam bath, and we want to convert it into work to do compression, right? A steam turbine. And we're going to realize that there's a problem, that we're not going to be able to get all the heat into work or the work into heat or vice versa. And it's almost as if some energy just magically disappears, that we can't use. And so we're going to learn a little bit about what that energy is, that missing energy. That we're never going to be able to convert 100% of heat into work and vice versa. And so we'll talk tomorrow on Thursday about what that is. Okay.